Perfect. Thank you very much. I would like, first of all, to thank you for this kind invitation. And I'm very happy to be here to share some thoughts about and some expertise that we have on condition monitor rotating machinery mainly, where we use digital twins and transfer learning, and a number of questions that will pop up. They were also included in the previous lecture as well. So here it is a short outline of my presentation. I'll start with a short introduction. I will talk about the transfer learning that we do for condition monitoring of rotating machinery with, let's say, specification in bearings, but this can be extrapolated in different other types of components and systems. And then I tried to concentrate a bit on the digital twins about diagnosis, prognosis, detection with some use cases, and I'll close up with conclusions and open challenges. And I will try to keep my time. So very short about Leuven. I'm coming from Leuven. It is a quite old university. It was founded in 1425. So next year we are celebrating the 600 years of existence of Leuven. It is 25 kilometers outside Brussels, so it was quite close from here. So we are part of the Department of Mechanical Engineering, and we are organizing sections. So we are the Mechatronics System Dynamics section, LMSD. We are 9.5 full-time equivalent academic staff. We have 2 research managers and 10 postdoctoral researchers. And we have approximately 100 PhD students, including 27 industrial PhD researchers. And we are active in different research areas: vibroacoustic, aeroacoustic, multi-body dynamics, smart system dynamics. And today our activities that I will talk about are mainly for structural reliability and uncertainty. And in parallel, we're a core lab of the Strategic Research Center for Smart Manufacturing in Flanders, which is called Flanders Make. So as a general strategy, which I think fit very well into the previous talk and to the symposium, we have the digital twins as a key, let's say, target. So we try to create it added value during all the phase of the lifetime of mechatronic systems. So from the design to the manufacturing to the operations, and we try to understand and control the dynamic behavior. So we're working with motion, vibration, and acoustics. And we adopt the model-based system engineering, machine learning, and digital twin concepts. So what we try to do in condition monitoring, we have the different complicated systems, which can be vehicles, can be machines, and we try practically to do 3 steps. First, it is to have fault detection, to see if there is a fault in our structure, then to diagnose, so to find what type of fault it is and at which component, and of course, the main target, which is the, let's say, the global target, and the dream, let's say, it is to perform prognostics, so to estimate the remaining useful life. Because practically in industry, what it is important, it is mainly to have 3 traffic lights. It is healthy operation, we keep on. There is an alarm, something should be more carefully done, and then now we have to stop. The condition monitoring, first of all, we start with sensors, so we have to gather data, and then there are different approaches that we can follow. First of all, we can extract some indicators, some diagnostic indicators to monitor, and this, till now, we can do that by signal processing. So if we have a very specific machine, coming also from a mechanical engineering background, we know the machine, we design the machine, we build the machine, so we don't need to forget whatever we know. So we can use signal processing with very dedicated tools, from Fourier analysis to cyclostationary indicators, and create very specific the monitoring and diagnostic indicators. In parallel, especially in the last years, there is another track from machine learning and deep learning where we can have end-to-end monitoring. Of course, the 2 concepts are more and more combined because in specific systems, as I mentioned before, we are designing the system, we have knowledge of the systems, so we don't need to start from scratch, but we can combine the 2 approaches. So if we have available data at high volumes, including the different types of fault type or the different types of faults, all the different operating conditions, so speed, loads, and temperature in a mechanical system, and they are correctly labeled based on a real ground truth, then we could really have a machine learning or a deep learning model, and then to have an end-to-end solution for the three different steps: for detection, diagnosis, and to look forward to prognosis. Unfortunately, the availability of data was promised. The last 20 years, we are talking about big data era, etc. But finally, we are not yet there. So practically, we don't have correctly labeled data, which covers all the volumes, all the fault types, etc. So despite the benefit of machine learning and deep learning, we have specific limitations. First of all, we are based on the assumption that both training and testing data, they are drawn from the same distribution, which in a real case scenario, this is not necessarily the case. And also they require significant amount of data, historical data with ground truth, so labeled data, which cover the full life of the machine, all the possible failures, all the different operating environmental conditions. This also is not feasible in real-world applications till now, although more and more the real machines, they have more and more sensors, they will gather data, but it is still very costly to gather the data, but not only to gather the data, but to label the data. Because very often companies gather the data, but then they don't put the specific experts to label them. So then they are not so useful data. And also the computational cost to start from scratch for each operating condition, for each failure mode, for each unit, it is relatively high. So as a solution to this, transfer learning has been proposed, where we try to learn a model based on the source, and then try to transfer all this knowledge from the source to a target domain. And in this way, we can shortcome, let's say, some of the limitations that were mentioned before. And there are different types of transfer learning. So you can do transfer learning in the same machine. So from one operating condition to another operating condition, from one work environment to another work environment. We can do transfer learning across different machines. So they are different but related. And there might be a data distribution discrepancy. But more and more, we're looking also to scenario, for example, that we can transfer from laboratory machines to real machines. So we have in labs, we have a scaled model that we can run different failures. We can do accelerated life tests, and then we try to use this information in order to train a model and then transfer it to the real case. Or we try to do, and this is the digital twin concept that pops up, to transfer from virtual to real. So to try to train a machine learning algorithm with a model that interacts with the real system, and then to try to transfer this model to the target machine. So this is practically a solution to the limited real historical data that we have. Because, and especially nowadays, we can have a lot of healthy data, but we don't have faulty data. For example, imagine in the aircraft engines, in gas turbines, you can have a lot of data that they are healthy, but hopefully you don't have even one that has fault, because you have performed maintenance earlier than that. So transfer learning is a possible solution, and we have here three cases. One case is if we have available data from the source, but no data from the target. And in this case, we could immediately, let's say, train a model in the source data, and then transfer it as it is and update and use it in the incoming data. This usually has low performance because the two systems will be a bit different. So it is a starting point, but it will not perform very well. And then as it was, and why practically there will be a distribution change or a domain shift between the two domains. And for this reason, the old model will not be able to be used correctly in the new system. The next step was something that it was mentioned also before, that we have available data from source, and there is a limited number of data from the target. And in this case, we can build a model based on the source data. Then we can, in a way, train the model there. Then freeze all the layers and retrain only the last ones. And then we can use this in order to we can use it then to the target domain, and we can perform in this way transfer between machines and operating conditions with a limited number of labeled data from the target. This has a higher performance compared to the first one, but still it is very case dependent. And then we have the third case where we have available data from the source. We have limited labeled or unlabeled data from the target. And then using transfer learning techniques like the domain adaptation, we can train the model at the source data and at the limited unlabeled data from the target, and then transfer it to the target domain. And this practically has a higher performance. We'll show some, let's say, results. We applied such approaches in wind turbines. So there was a competition in China where there was for blade ice detection in wind turbines. It was based on SCADA data, so we have 26 different variables from the wind turbines. And there were two turbines, turbine 15 and 21. And then we applied the domain adversarial neural network, which consists practically of three sub-networks. We have a feature extractor, we have a label predictor, and we have the domain classifier. And on the right, you can see the structure of this network. So we have the feature extractor, the discriminator, and the classifier. And we have the loss function that we train it on the source plus some target signals. And then we tried either to input a 1D line with the 27 variables. And we tried to evaluate also, please keep in mind that it is different to transfer from A to B rather to B to A. It might be different. So here we tried both of the cases, and we see that it did by comparing it with training only on the machine learning on a CNN network and transfer it as it is, or training it only on a limited number as the target data, and then using the domain adaptation technique, we see that we have an improvement using the last methodology, and we have around 70 to 80% of accuracy of score. And then we tried also to group a bit to use a bunch of data together. So here we put 10 sequences together, but this can be optimized further. And here we see that the results were a bit better when we use the DAN approach. And then we try to do transfer learning between different conditions. So we use some data sets that we have from our, let's say, simplified test rigs, where we have bearings that we can open them, create with manufacturing techniques specific size of faults, and then close them and put them back to the test rig. And we can apply in some balanced loads, and we can do varying speed or load conditions. Here it is a varying load condition and for different speeds. You use the dynamic adversarial adaptive network, which also has 4 sub-networks, let's say. And then we could do the transfer learning from a balanced load to an unbalanced load. And we see in the comparison that the dynamic approach provided some better results in this case. Also, we did transfer learning between different speed conditions. And we see again that the transfer learning with the dynamic approach improves the results in most of the cases, but still we see some some problems still when the speeds, for example, they are quite different. So when the two, because keep in mind also that in a system, when you have a run-up or you have varying speed conditions, different speed conditions, you might also cross resonances, so the amplitudes might be different. So at these points, we still see some limitations. And then we used also a publicly available dataset from also a simple, let's say, rotor dynamic test rig from Ottawa University, where they're doing some run-ups and run-downs in the speed. So we have different operating conditions, let's say. And here again, we compared 3 different types of networks, doing a transfer learning from what we called Huang, or it was a lady I met last week in a conference as well. So she was a PhD student in Ottawa University, and she did the measurements. So there we can see that with the transfer learning, the results are improved. In this case, and this is quite important, we try to do a transfer learning between machines. So from the Ottawa University to Leuven, and from Leuven to Ottawa University. But here what we should keep in mind is that the classes are 2 and they are the same. And in this case, the methodology worked quite well. While in the case that we have different fault types, so in this case, we have a healthy an inner race and an outer race. And in the second, let's say, domain, we have a healthy an inner race fault and a second inner race fault. So we have different, let's say, types of faults. In this case, the results were quite lower. And this is a case that it is quite important because it will not be always that the 2 domains have exactly the same classes, let's say. And then we did transfer learning between the 2 test rigs again under varying operating conditions. And here we tried also to include what we know from the signal processing point of view. So we tried to develop a physics-informed global local domain adaptation network. But here we didn't yet put the physics, which is based on the signal processing, in the model itself. So we keep it as a pre-process step. And now as a next step, we try to include it in the optimization scheme. And on the upper right, you can see some results with comparison with different methodologies, where the including, let's say, of the physics, which practically it can be seen also as a type of a model, can help improving the results. And also on the down right, you can see also how at the last layers we do the separation of the different, let's say, classes. And we see that in the last step, maybe I can use also the laser pointer. Here we see that the defects are better clustered compared to the other approaches. Then I would love to go one step further to the diagnostics, where we can call it diagnostics based on teacher twins, or we can call it simulation-driven machine learning. And there the idea was the following, that first of all, we had the challenge that we don't have fault data from the real cases. And also we might have categories mismatch. So we might have different classes at the target and at the source. So what we tried to do was to use a simulation model. Here we show just a very simple phenomenological model. So it is a mathematical model of a rolling element bearing, which was proposed by McFadden, who was a professor in Oxford. And of course, the approach is the same, but here the model can be more complicated or less complicated. And this is one of the conclusions at the end that will come up, that for different cases, we might need a simplified model or we might use a more complicated model. And depending on the case, we should select how complicated should be the model. But this does not mean a priori that we should go for the most complicated and for the most complete model. Even simplified models can also work in some cases. So here we have a bearing model where we have an outer race defect, an inner race defect, and a rolling element defect. And we use this to generate data and so we have the simulate data and we have real cases from different categories. And then we do transfer learning. And practically, we did transfer learning from simulations to real in order to do classification, so in order to do diagnosis. So we proposed a model where we have the source domain and the target domain, we have the feature extractor, and then we have another three sub-networks, a source classifier, a target classifier, and domain classifier. And we applied that in two publicly available datasets, the Case Western Reserve University, where we have 4 operating conditions for speech, let's say, and 10 categories of fault types, so inner race, outer race with different sizes. And also we use the dataset from the Paderborn University, which has also 10 fine categories under 4 operating conditions. And then we can compare different non-transfer models or transfer models. Here we had the 3 non-transfer models, the MLP, target-only convolutional neural network, or convolutional network with 2D inputs, where we use the wavelet transform as an input. And also we tried to see how many data we could use. So we started from 20 real samples, and we went up to almost 200 real samples. And of course, here, the main idea is that if we had too many data, a machine learning algorithm would work perfectly. But if we don't have data and we start putting simulations, then we see that even with only 20 real samples and the simulations, we have already almost at 80% success. And then we go, as we add more data, the simulation based goes higher, but of course also the purely data-based increase as well, which was what we would expect. But in reality, we cannot start from that, because if we don't have the data, we can simulate them, and then the more data that are coming in and they are validated, the better will be the models. And here we can also see a feature visualization using the TCNE algorithm, where again we see that we have a clear clusters of the features based on the proposed method. Here we see the different types of faults that they are clustering quite nicely. Then we compared also different domain adaptation models. So we had the VGG16 transfer, the adaptive already. Okay, the adaptive batch normalization and the maximum mean discrepancy. So we have the different conditions, and again with only 40 real samples, we're able to achieve quite nice results. Then in another digital twin framework where we have the physical entity and the virtual entity, and we have transfer of data, so we have simulation and sensors, as it was mentioned before. We can have the phenomenological model, and then the question would be always how accurate should be the model. And you see here some simulations and some real data, a comparison between real signals and simulated signals. And here we used again a model, a simulation model, and the signal processing in order to combine that with transfer learning. So we have on the upper side the simulations, on the lower side the real, and then we bring them all together to an adaptive domain adaptation network. And there we tried that with, again, an LVL dataset of varying speed conditions. So we see the measurement of the simulations, that they correspond quite nicely. And we can apply these approaches and compare it with other methodologies. And with the proposed approach, we have quite nice results in classification. I think now it is 25. I have spoken 25. Okay, that's good. So here we have the classification, let's say, and we can see that for different classes, we have quite good results based on the proposed methodology, and we see that also the types of the defects are quite nice clustered here. Also at the end, we do also a check of the distances between, let's say, the target domain and the source domain, because they are theoretically the transfer learning tries to build the two domains together as close as possible. So we measure also the distance between the classes, and we see that based on the recently proposed methodology, the two domains are quite shifted closer together, and for this reason the methodology works better. And we apply that also on the Ottawa University dataset, where we have again varying operating conditions. We see the measurements and the simulations that they correspond quite well. And then we can apply the same methodology, and we see quite high accuracy F1 scores, and we see a nice split here in the clustering of the different data, the healthy, the inner race faults and the outer race faults. And we see also the maps where still there are some issues of misclassifications that we are working still there. Then this was for diagnostics. Moving to one step for prognostics. Again, we can try to do estimation of remainful useful life, which is the dream, let's say. It is the golden, the holy grail, let's say, because then you can link it, as it was mentioned before, you can link it with a control strategy. So you can reduce the operating conditions in order to be able to extend a bit the life. You can link it with a maintenance strategy, and in this way you can have the optimum possible maintenance. So in order to avoid the data hungry techniques, and because in order to collect a big data set, we need persons of high experts to label the data, and this will be high costly. And we can replace that by simulation data sets. As I mentioned before, they can be phenomenological models, but they can be also multipody models. And then you can add more and more accuracy to the model. So you can move to put aging models. You can, and then the question is how complete should be the model. Of course, in the simulations, there will be still a kind of mismatch between the simulations and the real data. And for this use, the transfer learning can solve this problem. And also, it is important not only to work on steady operating conditions, but also on varying operating conditions, for example, varying speed conditions. But this is what we see in reality, in industrial robots, in wind turbines, in servo motors, etc. And we can use the speed or the load as context, let's say. And you will see that in different domains, we use also often different terminology. So in computer science, there is more and more use the term context-aware machine learning. But from the mechanical engineering point of view, the context was always in our, let's say, everyday work. So the speed and the load, it is something that you know a priori that you build your machine to operate at different conditions. So there we created a methodological model where it takes into account the speed, the load, the excitation of the natural frequencies, the measurement noise. And then we build a methodology where we have phenomenological model and some real healthy signals. So we do a kind of a model updating of the model based on the real signal. So we do the tuning based on the healthy signals. Then we do an anomaly detection. So we detect that now there is a fault. We get some faulty data that they are still non-labeled, and we try to represent in a way the degradation curve. And then based on that, we can fire and create a number of simulations, which we use them in order to train a model. So we have then the labeled real data, we have the simulations, and we do the domain adaptation, and finally we can estimate the remainful useful life. So in this case, we try to build a kind of a simplified model for the degradation and for the relation of the vibrations with the speed. So we have a part that represents the damage and a part that represents the influence from the speed, which of course it is a very simplified approach, and this can be further extended. And then we do, in a way, the the matchmaking between the synthetic signals and the real signals. So a priori, they will be different. So we try to do an optimization, practically a model updating, in order to bring the simulations as close as possible to the real signals for the healthy condition. Based on that, we can define a health indicator. So we have a part that it is practically a model updating or a pattern recognition. And then we create a new health indicator, we track it in time, and we can put some thresholds, and we do the anomaly detection. And after the anomaly detection, we take some measurements in order to try to create a first indication of the propagation of the damages. And we can extract some characteristics of the degradation of the aging model. And after that part, we can, let's say, create a number of trajectories, of damage trajectories. And based on these trajectories, we train the machine learning algorithm, and then we feed up the real data, and we can estimate the remaining for useful life. So we use the domain adaptation neural network for that, for the domain adaptation. So as the source, it is the synthetic random failure data, and the target are the real data. And here we can see a schematic of the model where we have the raw signals, and then we try to put as embeddings on the input layers here. We have a feature extractor. We have here the information from the raw signals, but then we try to put time information. So in a degradation system, you don't expect that the system will self-heal. So you can take the information that is time related. So one sequence is coming after a sequence, and the system should not self-heal. And on the other hand, we can have embeddings from the speed information. So from the natural language process model, we try to use some approach in order to encode the time measurements and the speed measurements. And we applied that on some random failure tests that we have from Flanders Make. So we have a fleet of test rigs that ran up to failure, and they were stopped up to peak of vibrations, and we, in a way, stop them or cut the data sets. So they are up to 15 Gs. So they are all ending at the same point. So the remaining for useful life, it is set for all of them. So then we had 6 random failure tests. We set the 15 Gs at the end of life. And here you see the speed and the real vibration signals. And we apply the methodology. We have an anomaly detection criterion. So we have the healthy data initially, then we have some standard deviation to detect the anomaly, and then we have, let's say, the anomaly indicator. And we said that after 3 consecutive points, we should create the anomaly. Then we have the part that we learn the degradation curve. Then we create the simulations. We do the training of the model. And finally, we do the estimation of the remaining for useful life. So practically here you see a line, which is the blue line, which theoretically it is the real rule, which is not absolutely true, because here the assumption it is that the system degrades linearly. But this is still now the main assumption that it exists in literature, and we're working also on changing this assumption. And then we have the red line that there is an estimation of the remaining for useful life for the different, let's say, types of bearings. And here we can see, let's say, a conclusion table where we have, if we use only the CNN networks or a DAN network without inputs from the time and the speed, then with inputting the time context, and then inputting both time context and speed context. And we see that by putting more and more information that we have, so the time information and the speed information, this improves our results. So now we're working also to extend that to take into account load and temperature, so more operating conditions. And here you can see also that based on the new model, the data and the different operating conditions are quite better, let's say, split in the map. And then I would like to go to the final point, which is in another way of building the digital twin. So in the previous two, let's say, versions of digital twins, the model was a simplified phenomenological model, or it could be a multi-body model, but there is also the possibility to create a purely data-driven model. So we can use a generative AI to create a model and then use it as let's say, the digital twin. So here we use this approach where we have a random signal, then we have a generator which tries to create a fake signal, and we have the real signal from the other, let's say, branch. And then there is a critical model that decides if the two signals are coming from the same distribution or not. In this case, we use only healthy data, and the target is to obtain the continuous distribution of the healthy data from a well-trained generator. So practically we have the random signal, the generator, and we create, let's say, a distribution of the healthy data. And this will be practically our digital twin, which in this case will be a digital twin which generates only healthy data. And then we can build an anomaly detection indicator or a fault detection indicator based on the discrepancy between the testing data and the closely healthy signal that can be generated. So in the unorgan approach, this model can be trained and by multiple time sampling, or we can find this close approximation by the multi-time sampling. In the first unorgan model, we built a kind of an encoder establishing the mapping between the signal, which is here, and the noise that it is here. So we have, again, a loss between the signal and encoder and the generator, and then we have the critical model to build the full methodology. And how to form the indicator? We use both cases. We use the Euclidean distance in the signal space and the Euclidean distance in the feature space. And on the right, you can see, for example, a real signal and a signal which is generated by the gun. So you see that they are quite similar, and here we find the difference. And practically, in this way, we can generate the digital twin by purely data. And then we used a thresholding strategy. So we built an anomaly score. We built a thresholding strategy. First of all, we have to understand which is the distribution of this anomaly score. And we can have a library of distributions and do some statistical tests in order to decide which distribution we should use. And based on this specific distribution, we can set a threshold. So we apply this methodology in, let's say, back-to-back test rig. It is a gearbox test rig that runs Axeri Live Test. It is in University of Ghent. And here, in parallel with the degradation, we capture also images. So we have also a camera to take the ground truth. So we are looking to the flanks of the gears to see when the fault starts. Because in all the methodology, and from signal process side, and from machine learning side, each researcher, each group can claim that I find the data earlier and earlier. But the case it is in degradation tests, there is no real ground truth. And in this case, we try by a camera to have a first, let's say, ground truth when the first fault will occur. And this will be our basement to evaluate all the approaches after that. So we used a number of signals from the beginning, 19 signals to train the encoder and the methodology. Of course, they are quite limited, as we see. And of course, we try still to evaluate if really the model is learning with so small number of signals. And then we apply on the different data that are coming in. Here we can see again the performance of the signal generation. So we see that we have the real signals and the generated by the GAM and the difference. And here they are different healthy signals. And then we have the anomaly score. We build the distribution. We do the distribution fitting. And then we have the cumulative distribution function. And based on that, we build a threshold and we can detect the faults. So here we have our threshold. We have then the indicator, and practically somewhere here we will detect the fault. We see still in the indicator a number of peaks. The problem is that in specific tests, there was a continuous loss of torque. So you see here from time to time there is a torque loss, and they should stop the test and readjust the torque. And this has as a result to create these drops because they are not steady operating conditions. Until now, we have not taken into account the different operating conditions. So if we see based on the proposed methodology, we have these, let's say, anomaly scores, we have a threshold, and if we compare it with a simple autoencoder, and we see that this methodology works better. Here we can see also assume exactly the place of the threshold. We see that there is some fluctuation, so depending on where we put the threshold, we might lose some points, but then there is a relatively monotonically increasing of the indicator. And practically the dream of in condition monitoring, it is to have a diagnostic indicator that either goes consistently up or consistently down, and this way you can connect it in a way with the severity of the faults, and then we can do prognostics in a more consistent way. So here, this generative adversarial network is able to help in realizing anomaly detection. And now some general comments. The transfer learning is able to, let's say, transfer knowledge from source domain to the target domain. And this is a nice way to solve the problem of lack of data. The computational power and time can be drastically decreased by leveraging all this pre-learned knowledge. So if we have source domains, we can get all this information and transfer it. We can transfer information between operating conditions, first of all, environmental conditions and machines, because the critical point, and this is also discussed, for example, in wind turbine parks, that you might have one wind turbine which is fully equipped with all the different sensors. This will be the leader of the flock. And then you build a very nice model in this leader of the flock. And then you transfer this model to all the other wind turbines. And this is the same can be in a fleet of cars, in a fleet of trains, etc. That there is one unit that is fully equipped with expensive sensors, and then you can build a model there and transfer it to the others. So the digital twins, then as a transfer learning, we can also use the digital twins. So we can use simulations and which interconnect with the real data. So there is a continuously model updating to use the digital twins to solve the data scarcity problem. The digital twins can be either data-driven or physics-based or a combination of the two. So practically what in mechanical engineering it was the multi-body model plus something equal to the real data, and the something in the past, it was a nonlinear term. It was stiffness times a displacement cubed. Here it can be that we can replace this nonlinear term with a machine learning algorithm. And the key point, it is the complexity of the model, it is still case dependent. And this is the challenge to understand now how complicated should be our digital twin or our, let's say, physical model of the digital twin for that. Some open challenges, how to avoid negative transfer learning. When the transfer improves the results, so we always should target to positive transfer. How to select the source domains. How complicated should be a virtual model, and how the methodologies can be applied at the system level. So here, although in condition monitoring there is a sensor which gathers all the information from the different components, a number of research till now it is based on some measurements from a specific component. Now we try to go to the system level. And here you can see also demonstration we have a test rig with gearboxes, and we built also a digital twin of the specific gearbox, and using virtual reality, we can enter the gearbox and we can estimate. So here, but this is a different type of digital twin. Here we had a digital twin where with state estimation techniques, we can calculate the stresses around the gearbox, and in parallel, based on the methodology that I mentioned before, we can estimate the remaining useful life of the bearings in the gearbox. So here we have a virtual reality that we can enter in the gearbox. Here you can see also the drivetrain. We can enter in the gearbox. We can see the stresses and the forces of specific bearings and the specific gears. So practically we are extending this approach that in practice we will be able to click a button and see the remaining useful life and use this, let's say, model. This will be the digital virtual model of the digital twin in order to generate data or understand better the data. So here I would like to acknowledge, because all these results, they were coming, first of all, from my PhD students, which I would like to acknowledge all this effort and all this work, and the different components from the different projects from European Commission, from the Chinese Scholarship Council, from Flanders Make, from the Research Foundation Flanders. So thank you very much, and I will be happy to hear your questions. Any question or any remark?
Yes, question. Let's switch to question. How to balance between model simplicity and realism?
Till now, there is no real clear question. Initially, we had in mind, for example, for the bearings, to go directly for multi-degrees of freedom systems. So we had mass stiffness damper models with 10 degrees of freedom, but then we applied that, it works, but then we used in the simplified phenomenological models that it worked as well. So the question there practically it is if you have a representation of the physics, and if you have enough physics in the model that represent the problem, then you are okay. But it should be, whatever you use, either it is a training, if you use something for training, these signals that you use for training should cover the physics that you are searching for. Otherwise, the model will not work.
Other questions from the audience? Maybe Professor Barros? Yeah.
Just a live question. According to your experience, when transfer learning is good, is efficient? In which kind of situation is it possible to have
There is no global comment there. I mean, in all the cases that we applied that, we see positive learning. In the only cases that we saw some problems was when we tried to transfer from one speed to another speed, in case the two speeds, they were very different. And there, I have the feeling that it is that the speeds are very different, so the dynamics of the system is different excited. So we are crossing resonances or different resonances are excited. And for this reason, the information is different.
Maybe if I can, so maybe very quick. So actually, I'm not an expert in signal processing or mechanical engineering, but I have a question actually for a long time. So I know that in signal processing before we do like a lot of feature engineering, Fourier transformation, wavelet, like this. But right now it seems that people are replacing that just using deep learning model, right? So can you elaborate a little bit? So how can we compare?
Yeah, there will work in both cases. So practically, and that's why I mentioned the signal processing and that we don't need to start from scratch. So in the deep learning, theoretically, you start from a time signal. And the deep learning, in a way, you could use the same approach for a brain signal, for a heart signal, and from the signal of the bearings. But this does not really make sense. Because if in the bearing, there is a history of, or the bearing practically exists since a wheel exists. There are companies that they are working on the modeling of bearings, for example, SKF, the last 150 years. So in a way, all this knowledge should not be sent in the garbage. It exists. So the bearing will fail with 4 specific types of faults. So it will be an inner race, an outer race, a cage, and a ball. And they are based on the kinematics, you can know exactly what type of frequency you are searching. And then you can apply signal processing techniques to denoise the signals or to identify these weak signatures. and then you can use this information. That's why more and more they are, especially in systems that they are very specific or that you have mechanical knowledge of the design of the system, you try to combine both, so machine learning and signal processing. In other cases that maybe it is a very general grid, so there is a combination of different pumps, and then it is more the fleet level and is not the independent pump separately, maybe then a more machine learning or deep learning approach could be more appropriate. But the key message from my side is that if we have physics that we know, we don't need to forget what we know. We need to build on what we know and then try to answer what cannot be answered from the existing methodology.
So traditional mechanical engineer will not be replaced by AI. So their job is secured.
I think yes, it doesn't make sense to be replaced. So practically in parts of a human body, because in the digital twins, there are also colleagues that they work on digital twins of a human body. In the heart, for example, you cannot really yet model a heart. Yeah. And then machine learning can really be used to model components or of the human body or other components that there is no model already or there is not understanding of the knowledge. Mm. But if in electrical engineering or in mechanical engineering there is existing knowledge, we don't really to forget whatever we know and suddenly start from scratch because AI is a trend.
Definitely. At least we are sure that we are not going to replace our coffee break with an AI model, right? So it's outside. Right?